sorry, I start again. So good afternoon, everyone. Welcome to this webinar. To those that are in this room where I'm sitting, and to those that are online. And maybe Ilya can tell me whether at QSUN Westville it's just him, or whether there are more people there.
There are more people there. Let me turn on the camera.
Yeah, that would be nice to see who's there. Okay, we will see the camera when it comes on. Ah, okay, wonderful. Yeah, so the usual suspects, so to say. Hi, Shivani. Hi, Jan. How are you guys? Excellent. Very good. That's a very nice new institution, and also welcome to the other online participants. Today's speaker, famous Professor Marco Merkli, and we are very honored to have him in Stellenbosch. He's been here already for a week and a half, and will stay on almost for the whole of next week, or at least partially next week. Marco is originally from Switzerland, of all places, but he did his famous PhD in Toronto. And I don't know if from there you went straight to St. John's? Or...
Oh no.
Okay, over a few stations. He ended up being professor of mathematics in the Department of Mathematics and Statistics at Memorial University in St. John's.
That's
right. Yeah. And although he's a mathematician by training, he's a physicist at heart. Because he tries to do mathematical problems that have a strong physical implications, and also might lead to the prediction of new effects.
Of course.
And potential Nobel Prize. Yeah, so Mark, we are very happy that you are here with us this afternoon, and we are very much looking forward to your talk.
Thanks, Francesco. Very nice introduction, full of true things about my field. That's, I think, about the third time I've been visiting Francesco's group, a while ago in Durban, and my second time here, I think. And it's a great pleasure for me to be here, and also to be able to give this talk to you. And don't worry if you fall asleep, because then when I come next year, I can use the same slides, and you think, oh, it's a new talk. Okay, so I would like to talk about this here. I'm not reading the title. In fact, this is a collaboration with two friends of mine, Paul Paris of Missouri and Stéphane Demierre from Lille in France. And especially with Stéphane, I've been working over many years on many different things, kind of. And with Paul, this is my first collaboration. Okay, so Paul is definitely a pure physicist, and Stéphane is sort of a mathematical physicist. And so what I'm talking about is based on a preprint that's on the archive, and actually underwent one round of refereeing for a journal. And if you ever want to go and read up on this, you will be delighted to see that the whole paper is written like a poem, okay? Because Paul in particular is very artistic, he's also a musician, and he writes very nicely. Okay, so we're going to deal with the following setup. There is an optical beam, that's the horizontal line here, that will encounter sequentially a bunch of optical beam splitters. They're here this at 45-degree angle placed bars here. So an incoming beam hits the first beam splitter. The beam splitter also has an incoming light from this side. Then these two modes interact, and then of course something goes through this way from sigma, and something goes through from the incoming row, and then this is a repeated sort of scattering process. And not that I know much about experiments, but one of these interactions here is in the top right-hand corner. There's a picture of that, how this is actually realized in the lab. So you do have beam splitters where you have two incoming beams, they interact, and then you have two outgoing beams. Okay, and what we would like to figure out is what happens to this incoming beam after many interactions with these beam splitters. Okay, so this is an open quantum setup. The system is the incoming beam that undergoes repeated interactions with the sequence of beam splitters, which is the reservoir. And the question is, what's the asymptotic state of the outgoing beam? And as you know here, as good as I, if not better, that is an open system, as I said, so a quantum system which interacts with an external environment. And open systems are, of course, important virtually everywhere in physics, including in quantum biology. And people here work on quantum biology. So this is a picture of an open system in light harvesting complexes. So this slide is just to say that this is within the wider context of open systems. And since, in general, no quantum system is totally isolated from the rest of the universe, every system really is open, and there needs to be some theoretical framework for treating such systems, and this is the open quantum system theory. It's important in optics, quantum information chemistry, biology, and so on. This system has a special structure because, as I said, the incoming beam repeatedly interacts with a bunch of beam splitters, and so this repeatedness of the model gives a certain structure to the whole dynamical setup. Okay, and it's called a repeated interaction or a collision model. And in a picture, it is summarized like this. A system interacts with the first part of a reservoir. So this here is a reservoir. The reservoir is a chain of individual elements, which are called ancillas. This is ancilla number 1, 2, and so on. And after the interaction of the system with the first ancilla reservoir, the reservoir is shifted by 1, and then the system interacts with the second ancilla of the reservoir, and so on. Okay? This can be cast in terms of quantum circuits, and there's a lot of research in general on repeated interaction or collision models. In fact, right now, while I'm here, I'm working on something like that with Graham and Francesco. Okay. So the main question in open systems is, well, if you have a system of interest, which would be our incoming beam, interacting with a large other system, which is the reservoir, which is the sequence of beam splitters, what is in general the dynamics of the system alone? Okay, and the goal of open quantum system theory, one of the goals, is to find sort of effective equations of the system alone that encode the interaction with the reservoir. And sort of openness of systems is linked to decay versus oscillation in the dynamics. So let me try to explain this. Suppose we have two parts of a system, of a complex, a system part and a reservoir part, and suppose that these are, just for illustration, two boxes, a left box and the right box here, and suppose that there is a channel between these two boxes, and you have a particle in the system part, which is the left part, and you kick this particle, and it will move around, bounce around in the first box, and eventually it will happen to see the entrance of the channel. It will go through this interaction channel and switch over to be in the right part of the system reservoir complex, okay? And in this situation, the system and the reservoir, they're sort of comparable size. And so if I'm only interested in measuring or observing or looking at the system alone, I started off with a particle in here in the system, and I see, oh yeah, it's still there, it's moving around, but suddenly, because of the interaction with the other part, the particle is gone, and I will see, oh, the particle has disappeared. But then, of course, the particle does the same thing here, it bounces around, eventually will find back its way through the interaction channel and come back to the system. So if I only look at the system, I would see my particle is here initially, ooh, then suddenly it's gone, and after a while, oops, it appears again, okay? And this will go back and forth like that. But what happens if these two guys are not equal partners? For example, if the reservoir is very big, well, still initially, if I only observe the system part, I have a system, then the particle disappears, it's gone. but because of the big size of the reservoir, the particle will spend a lot of time in the reservoir, and I will have to wait for a long time to see it reappear in the system here, okay? And so if the reservoir becomes bigger and bigger and bigger, then this could give rise to irreversibility in the dynamics of the system alone, right? Because the particle could be here, but after, I don't know, 10 seconds typically, it's gone out and never comes back. So if something turns big, that in the dynamics of a local thing can turn oscillatory behavior into decaying behavior. And that's typically what you observe in nature, of course. There's all kinds of dissipative effects because systems are coupled to big reservoirs. So that was sort of a classical physics picture, but even in quantum theory, it's the same thing, right? If you take two spins, you make them interact, and let's say there's a total excitation in the two spins, and you start off with the left spin to be excited and the right spin not, and then they interact. These models are explicitly solvable, very simple. You see that the probability of finding the spin or the excitation on the left side I put the excitation first here, so the probability starts at 1, but then it oscillates and is periodic because the excitation is passed back and forth between spin left and spin right. These are equal partners, but if one of the components of this bipartite system is very large, for example, if the spin now is replaced by an atom, or by a two-level system more like, and this is placed in the electromagnetic field, as you know, if you have initially an excitation in the atom, then this excitation typically decays. The atom will go down to the ground state and emit the photon, and this photon will never come back, and the excitation has this irreversible behavior going to 0. So, oscillation versus decay. In open systems, where one part of the system is very large, we typically have irreversibility. And one of the, I guess, very fundamental and important dynamical features is this thing called return to equilibrium, right? Typically what people say, if you have a hot cup of coffee in the morning and you put it on the table and you wait for too long, then the coffee will cool down to the room temperature. So initially, if you have a big system, open system context where one part is big, in a good contact where you can exchange energy with a cold initial system, and you wait for a while, well, then eventually they will end up both at the same temperature. And if I look at the system alone, this is an irreversible process. I have thermalized from a cold state to a hot state. Okay? Of course, it is important in this picture that you know that your reservoir initially is given at a temperature T. Only then are you not surprised that after a while the system itself will also be at that temperature. So it inherits some properties of the big system, namely here the temperature. And the main message about our model, the main result sort of is this. In fact, that's maybe a bit surprising. What we're showing is that even if the beam splitters, or the incoming beams, sigma of the beam splitter, are not in equilibrium, the beam that passes through these beam splitters, after many passages, scattering passages, will become an equilibrium state itself. Okay, what I'm saying is, that wasn't very eloquent, but so sort of, even if this, in this situation, even if this here was sort of a random system that wasn't in equilibrium at some temperature, what I'm saying is that in that specific model of the beam splitter will thermalize because of the contact with a non-equilibrium reservoir. And so the temperature at which it will thermalize depends, of course, on the property of the reservoir. But it's fundamentally different from this. This is sort of, you see, this is a little perturbation from a equilibrium situation in that the initial state here is almost a global equilibrium, except that a small part of the whole system is not in equilibrium. And then it's like a perturbation thing saying that, well, if you deviate just a little bit initially from equilibrium, you will go back to equilibrium. But this is much different. Here really the main part of the system and reservoir universe is not at all in equilibrium, because the main part is the beam splitter because it has so many elements, and yet the open system will be driven to equilibrium. Okay, that's the main result. So let's see how we calculate this or how we deal with this. So we have optical modes, whatever, oscillators. We have a system mode given by creation or annihilation operator A that satisfies the usual bosonic relations. And we have independent beam splitters, right? Would be beam splitter 1, 2, 3, and so on, with their own creation and annihilation operators B. And then the interaction between the field A and B, as it happens in one of these scattering processes, people know how to describe this. It's given by this unitary operator here. So this S is an operator that tells you that whose input is the state of two beams, two modes, an A mode and a B mode. And then when you act with S on that, you get the output, what comes out after the interaction has happened in this beam splitter, okay? So there is one, okay, so you see that it's the exponential of something, and in this something, here the beam splitter excitation is absorbed and transferred to the traversing mode, and here it's the opposite effects. So it exchanges one excitation. And there is this parameter lambda on top here, and obviously this is a number. If lambda is 0, then this S is just the identity, which means the two beams just go through and don't interact. And if lambda is non-zero, then something happens. And it turns out, people know that, you can calculate that, oh, this theta should be a lambda, I'm sorry. The sine of this lambda is the reflection coefficient, and the cosine of this lambda is the transmission coefficient. So once again, if lambda is 0, and this theta, which should be the lambda cosine of 0 is 1, so the transmission is 100%, of course, okay? So at each step, when the beam encounters a beam splitter, this map S has to be applied to see what the outcome is. Okay, so then this whole scattering experiment is described like that. If the incoming density matrix of the system is rho, and the beam splitters are always in the state sigma, then the outgoing state of the mode after one scattering event is given by this density matrix rho1. That's the density matrix of the A mode after the first interaction. What you have to do? Well, you have to make them interact via S1. S1 is simply this operator S, which acts on the incoming mode and the first previous slide. Previous slide.
Yeah, I'm not really familiar with this setup, but is this lambda times the parentheses, is this Hamiltonian or not?
It is, yes. Yes. This map is a unitary map. You could also write an I here,
yeah,
and minus I times that, and then it's I times a Hamiltonian.
Okay, yes.
Okay, so then after the first passage here, the rho has turned into rho1, and that of course is the in state or the in wave for the next scattering. So in the next scattering, the incoming state is rho1. Again, it will be seeing the incoming state of sigma from below for the second beam splitter, and then those two engage in interaction. And you get the outgoing state, rho2, of the field, of the mode after two passages, and so on. And you can do this k times. And so the kth element, the kth output is given just by taking the previous output, the k-1 output, and then acting according to the beam splitter dynamics last time, okay? And because of this repeated interaction thing, this is actually obtained by applying a single map L, dynamical map L if you wish, one time step map L k times to the initial state. This rho is the initial state of the incoming beam. and after k interactions, the outgoing state is rho k, and it's obtained by taking the in state and applying a map L times to rho. And of course, this L is given in terms of the S, right, by this procedure, and you can just read off what it is actually, and here I wrote it down for you. This L is just a single step interaction, given in the following way. The A mode is in state rho, the B mode is in state sigma. You make them interact according to this one-step unitary operator. You trace out the B mode, and then you get the outgoing, you get result after one interaction. Okay, what we want to do, as I said, is we want to see what's the asymptotics after this guy here has gone through many, many interactions. So technically, we want to take the limit of this map L applied k times to the initial state. Okay. We're going to calculate this limit explicitly, but in a sort of a little indirect way. Namely, instead of calculating the density matrix itself, we will calculate its what's called characteristic function. Okay, so what is the characteristic function of a mode? So if you have a density matrix of a mode A, then you can look at the average in this state rho, the average of this operator here, which is called the displacement operator. Z here is a complex number, and this is A and A star are the creation and annihilation operator of the mode. And so this is the average of some operator, observable, and this observable depends on Z. So this is actually a function, it depends on rho, of course, and then otherwise it's a function of Z. You know, input is a number Z, output is a number which is not an operator, but a number, because you take the average here, okay? And it turns out that this function, chi of z, determines 100% the density matrix rho. You can see why this is, right? Because, for example, I can, from this, reconstruct all kinds of averages of all observables I wish. For example, if I want, you know, I can take the derivative with respect to z here. If I take the derivatives with respect to z, then an A star comes down. I can take 5 derivatives with respect to z, then 5 times the A star would come down. And then I can take derivatives with respect to the variable complex conjugate of z, then the A's would come down. And so by taking derivatives of z and z bar, and in the end, putting z and z bar to 0, I can create any average of any polynomial in A's and A stars traced over with respect to rho. And so I can recreate the state 100%. So knowing this function is the same as knowing the state rho itself. Okay. So what we're going to do is we're going to calculate the limit of this here for rho k when k goes to infinity, and then once we have this, we can reconstruct the state, or at least its properties. Okay, so there are special states of optical modes, which are called Gaussian states, and the state is called Gaussian if its characteristic function is given by a Gaussian function in z. Okay, which means that this would be a function of z, e to the something, and this something should be at most quadratic in z and z bar. Such a state is called a Gaussian state. And Gaussian states are actually important, and they show up in mathematics, and I also think in physics all the time. And they are, because they're very, it's like a Gaussian random variable has a mean and a variance, right? Same thing here, except you have two variables here. You have z and z bar if you wish, whatever. But if a state is Gaussian, it's characterized entirely by its mean, so to speak, which is called the displacement vector here. It's the average of A and the average of a dagger. That's a vector of two components, numbers. And the covariance matrix, which is a 2 by 2 matrix with entries that are, whatever, called covariances of A and A star. Okay, but my point is that if a state is Gaussian, then you know, I only need two objects to characterize it, the displacement vector and the variance. Okay? And the example of a Gaussian state is a thermal state. Here's the thermal state, that's the Gibbs state, Gibbs equilibrium state at inverse temperature beta. Here you have the Hamiltonian of the mode. I guess the frequency has been put equal to 1. And this is the partition function. This is a Gaussian state. If you calculate the characteristic functional of this, so you take the average of this of a displacement operator carrying z, it will be a Gaussian function with and the corresponding displacement vector and covariance are given explicitly by this. Here, this state has covariance vector 0 because the average of A and the average of A star in rho is 0, remember, and this vector is built by these things. So the delta is 0 here. Such a state is called a centered state, and you can calculate explicitly this covariance matrix A, and it turns out to be off diagonal. And of course, the only thing that plays a role here is the inverse temperature beta, and the off diagonals carry this temperature in this specific average number of particles that shows up in the off diagonal. So that's a very famous Gaussian state, the thermal state. Okay, now this is the calculation, the basic calculation of this whole paper. I was going to do it on the board there, but I will spare you. This was going to be multimedia, right? Electronic and by hand. But I'm just telling you, it's a short calculation to find the characteristic function of the state rho k, where the beam has gone through k directions with k beam splitters. How do you calculate that? Okay, let's go. This is what we want. The definition of this characteristic function is, well, take the state, it's rho k, and take the average of the displacement operator with respect to mode A, there's an A here, and with the variable z. Okay, now we know that rho k, as we have constructed it before, was applying k time the operator L to the very initial state. Okay? So that's just the definition of rho k here. And now I say, well, applying L, the operator L k times, is applying first the operator k minus 1 times and then a last time. So I write it like that. And then I use the definition of what L was. Remember what L was? L took the input, cancelled it with sigma, and made the two interact according to the beam splitter interaction. That's what I wrote here. This here, L, is applied to this, so I copy this state here, I tensor it with sigma, and I make these two guys interact with S. And then I have to trace out the beam splitter, because I'm only interested in the system dynamics. So that's that. This part is this here. And now I realize that I can write this as a trace over the full space of two modes, the A and the B mode. Namely, if I, instead of D, write here D tensor 1 on the B mode, I can take these traces together. And this operator I copy here, and this guy has to be tensored with 1 on the right-hand side. Hope this makes sense. And now I sort of can pass from the Schrödinger to the Heisenberg picture, because see, now I have a trace over the full space. I have a matrix S that acts on the full space, and so by cyclicity of the trace, I'm allowed to take this S over here. That's what I did here, and then you see that I can realize this as the Heisenberg dynamics, so to speak, on this observable A, and the state is still here. Okay, so now I'm going to calculate this orange part here. And because the action of S is so simple in that it exchanges only one excitation between the two beams, this is very easily calculable, and it is of product form. So if I calculate this, what I get is the displacement operator on the A mode times the displacement operator on the B mode. And the only action, well, is actually that I also have something on here. Here it had a 1, but is that this Z undergoes a transformation, namely it's now Z times a number C for the A mode and Z times a number S for the B mode. And this C and S, they are respectively the cosine and the sine of the interaction constant lambda, okay? Remember this lambda was sitting in the S, its cosine is the transmission coefficient and its sine is the reflection coefficient, okay? So I use this, look, this yellow stuff here, this orange stuff is now a product of two things. Why was I interested in this again? Because this is sitting in here. So this now can be replaced by this product of the two D's, okay? And so if I have a product, a tensor product of the two D's, this goes nicely together with this tensor product, and the trace splits actually. Okay, so that's what I did, that's what was written before. I have replaced now the S star S thing with this. Now these two guys go on the same tensor factor. Sigma and dB go on the same tensor factor, and the trace splits into a product of two traces. Okay? So if I write everything again in terms of characteristic functions, because this of course is the characteristic function of the state rho k minus 1, and not at the number z, but because of the interaction at the number cz, and this is the characteristic function of the state sigma at sz, then I get this. So I have iterated sort of one time, I figured out that the characteristic function of rho k is that of rho k minus 1 with a modified c, tensor something that comes from the reservoir. And now I just iterate that, right? I'm not interested in rho k minus 1. I want to iterate this until I get down here to the initial state, because in the next state it will be rho k minus 2 and so on. So I do this k times, and each time I get an average of a rho k with index 1 less, but 1c is added, so it accumulates to get a power c to the k. And these guys, they accumulate also factors, okay? And so just iterating this leads to this formula. It's actually immediate. If you don't see it, just takes a second to realize. Okay, and again, so this is the characteristic function at time step k. And I would like to take k to infinity because I want to see what happens after very many passages of the mode through the beam splitters. If I take k to infinity, what happens? Well, I have a first term that depends on k. What happens to this one? Dr. Pleasance.
Sorry, repeat the question.
No.
What happens if?
Yeah. Sorry. Okay, the c is a cosine of lambda.
Yeah.
I take the kth power of that, and I want to see what happens when k goes to infinity. Well, c is a number that, unless lambda is very special, like 0 or pi or something, this number is strictly less than 1. Okay, but of course I'm not looking at the case 0 or pi because this corresponds to total transmission or no transmission at all. I'm looking at something in between where the c then really is the number between 0 and 1 in absolute values. And if I take the kth power of that, this goes exponentially quickly in k to 0. Okay, so as k goes to infinity, this ck, it's just a number, goes to 0, and so I have the characteristic function at 0. But the characteristic function at 0 is just a trace of rho, and that's 1. So this factor goes to 1 in the limit. And so I only have to say, well, what happens to this part? And all that depends on k is that the number of factors in this product here, right? And so what you get as k goes to infinity is the infinite product here, because this goes to 1. So that's the result. And I wrote down for you again explicitly what this, yeah, that's right. This is written here in terms of the characteristic function of the incoming sigmas of the beam splitters. And if you write out this explicitly, this is the average of this displacement operator in the state sigma. Okay? You have to do a few estimates to actually see that this infinite product converges and stuff, but that can all be done. Okay, so we have the limiting characteristic functional, and by what we said before, this will correspond to exactly one statement density matrix, and that is our limiting, our asymptotic state of the mode that went through. And all that follows now is a discussion of properties of this here, in terms of, well, physical things. So here I wrote again the final expectation functional, the final characteristic function. The first thing you notice is that if you look at what objects play a role here, well, the initial state rho has totally evaporated, right? That was sort of in the first factor here. Rho was in here, but because I took k to infinity, this tended to chi of 0, which was 1. So nothing else depends on the initial state. So that's the first thing that you notice from this formula. So the final state is independent of the initial state. But of course it depends on the reservoir, in the sense that it depends on what the sigmas were that were the reservoir states of the beam splitters, and depends on the transmission coefficient, or in other words, on the interaction between the system and reservoir. The second thing you note, you can calculate from this, again, as I said, by taking derivatives with respect to z and z bar, and then taking z equals 0, you can calculate the average of A in the final state, and you see that it's actually the same as the average of the annihilation operator of a single mode of the beam splitter incoming, related by a factor which depends on the interaction coefficient lambda. Okay? And in particular, you see that if your beam splitters are centered initially, so that this is 0, well, then your outgoing state, asymptotic state, will be centered as well. Okay? You can also look at the covariance matrices, and you can easily see from the formula above that the covariance matrix of the final state is the same as the covariance matrix of the state segment. Okay, so that is one thing that's going to be inherited by the final state. Namely, the final state will have a covariance matrix which is inherited from the sigmas. Because it has interacted so many times, it takes on that covariance matrix. And if the incoming beams of the beam splitters are centered, then these covariances actually just reduce to the average number of particles in the states. And so the conclusion is that the average excitation number of the outgoing beam is the same as the average excitation number of each of the beam splitters. Okay, so that's something that's inherited by the outgoing state, and one could call it an equipartition of photon number, because the photon average number is taken on when you interact many times. Okay, and you can see from this formula again, this is all just by looking at that. See, I don't have to evaluate this explicitly, I mean, good luck, right? It's an infinite product. But just by looking at this, how it behaves with respect to derivatives and so on, all of these things follow easily. And what follows in particular also is that if the beam splitters are in a Gaussian state, so they would be given by a certain covariance matrix A and delta, the displacement vector, then the outgoing asymptotic state of the beam is also Gaussian, with same covariance matrix, we had this already above, and with displacement vector which is related, which is a multiple of the displacement vector of the beam splitters. And if sigma is a centered Gaussian, so it's not only Gaussian, but it is average 0, then it turns out by the previous point that the outgoing state of the beam is the same as the state of each of the beam splitters. Okay, so that is sometimes what people call homogenization, because if every beam splitter is thermalized and your initial beam is whatever, runs through it many times, it will also get thermalized. Return to equilibrium. Because in this situation, you know that the reservoir is in thermal equilibrium because each beam splitter is in thermal equilibrium. Then the initial state of the incoming thing will be driven to equilibrium state. So this is, again, return to equilibrium, happens also in this state. But it is not true that the outgoing asymptotic state of the beam that goes through is always Gaussian. You can found examples. For example, if the beam splitters are in a state, a Fock state with a definite number of excitations, then you can show that what goes through will asymptotically and come out asymptotically will not be Gaussian. Okay? However, and that's sort of the main result, as I told you at the beginning, you can look at what happens when your beam splitter transmit a lot, okay? So when lambda is small. So what we just calculated was the asymptotic state of the system as it went through many interactions. And once you have that asymptotic state, it will depend on the interaction strength. And you can expand this asymptotic state and look at the lowest order in interaction, and then look at first order corrections and so on. And the lowest order is called, let's call it like this. So that's, you waited first for a long time, infinite time, and then you get a final state. It depends on the interaction strength. And if that is small, then this is the main state. And because, you can expand the characteristic functional of the final state in terms of this interaction coefficient lambda. And whatever, the first coefficients are like that. And if the sigma is centered, oh, sorry, this phi is a plus a star, then this term is 0. The exponent here is something that is a constant and something of order lambda. And you can take the limit to 0 and you will get the characteristic functional of this main term here. If the beam splitters are in states for which sigma is not centered, then this limit, this expansion here is not valid. As lambda goes to 0, we get something which keeps oscillating. Anyway, but for centered states of the beam splitters, as I said, this is 0, and then you can take lambda to 0, and all that stays is the exponential of a single term here, the exponential of a variance. And then you see that this is Gaussian. Okay? So no matter what the sigmas are, if they're centered, to lowest approximation, the outgoing state will be Gaussian. Okay? And so, to first approximation, if the transmission is good at each step of interaction, the outgoing state is going to be a centered Gaussian, and it has inherited the covariance of the reservoir. Even though these guys are not necessarily Gaussian, they're anything, just anything centered. So this is sort of a Gaussification. Anything you send in the end will be Gaussian. Yeah?
So this, make sure I get it right, the lambda being small means the system beam is not getting reflected a lot.
Yes.
The
lots is transmitted.
Yeah, the sigma, okay.
Yes.
Okay, and then if you say it's a centered Gaussian, does that mean it's a thermal state?
No.
Oh, okay.
Well, sorry, what? Centered Gaussian?
Because you said earlier the main result is even if
Yes.
the reservoir is not in thermal
Yes.
equilibrium, you find that the system goes to thermal equilibrium.
Yes.
Okay.
Yes, that's correct. This is what I was just going to say next.
Okay.
That is actually correct. Okay, but my point here is that the sigmas don't have to be Gaussian, but you can still calculate this covariance matrix. It just doesn't totally determine your state, but it's part of the state. But that covariance matrix will be the determining characteristic of the final state to lowest order approximation in the interaction. You know, it's not silly to look at this lowest order approximation because I have a second to talk about that. It's almost at the end here. So there's two limits here, okay? There's a limit of taking many interactions and the limit of taking small coupling, okay? But the point here is first you take many interactions, in fact infinitely many, you get something and then you take the lowest order in the approximation. For instance, in the situation of return to equilibrium, right, where you have the cup that you place here and you let the whole system interact, the whole system will become total combined equilibrium. So you have waited for a long time, so the equilibrium has been established. And then you look at what is this guy's, my cup's state alone. This will depend on the interaction strength. But you have first waited enough so that the equilibrium has been set in. And so then, to lowest order, when I take lambda equals to 0 of this state here, it will be the equilibrium state of this object, equilibrium with respect to its own energy. Okay? So this makes total sense to look at small coupling after you took t to infinity, or the number of steps to infinity. Of course, if you first take the limit lambda to 0, stuff's not interacting and nothing happens. Okay. Okay, so now is the question, when is this final state in first approximation an equilibrium state? Well, as I said before, equilibria are centered Gaussians. And it turns out that, if you look at this formula from above, if the beam splitters are stationary, that is, they're in a state which commutes with the total number of excitations, the number of excitations of each beam splitter, then automatically the averages of A and A stars are 0. And the covariance matrix of this A, because of this property, it will be off diagonal. And as I told you, Gaussian states are exactly those with 0 displacement vector and off diagonal covariance matrix. Okay, and so just stationarity of the beam splitters implies that you have approach of equilibrium of the beam that goes through. Okay, just stationarity. There's many states which are stationary but not equilibrium. Okay, that's the upshot. And that's the main message. This is in our paper. I quoted this here because to give you the feeling of that this is actually a piece of an artistic piece, because we wrote something like this. This is a proposition. I mean, no mathematician would ever write a proposition like that. It's a text, but not that you have to read it. But I'm just saying this paper is written in a very approachable.
Oh, sorry, can I read it to the end?
Oh.
But it doesn't rhyme.
Well, it depends on your imagination. You know, modern rhyming is not like the old way. Such as we are. Okay, so that's the main message. And here's the conclusion. Okay, we took an optical field mode, that is a harmonic oscillator, scattering through a series of beam splitters, and we calculate the asymptotic state. First of all, it's not clear that there's an asymptotic state, but there is one, and we calculate it. We see that that asymptotic state is independent of the initial state of the field, but it depends, of course, on the state of the beam splitters and on the interaction strength. We have equipartition of energy. Whatever comes out asymptotically has the same average number of photons that each beam splitter has. The output is not in general Gaussian, but if the beam splitters are in the Gaussian state, then so is the output. If the beam splitters are centered Gaussians, then you have homogenization. You have copied after many interactions, you have copied the beam splitter state to the output state. And if sigma beam splitters are in equilibrium, your output state is also equilibrium. But more generically, the output state is always equilibrium, even if the beam splitters are not in equilibrium, at least the lowest order approximation in the interaction, provided that the beam splitters are stationary, that they don't create anyway. Okay, and this is the paper as it is on the archive. And again, you see, I mean, look at this title, right? Yeah, there's no mathematician who writes a paper with such a long title. But why not, right?
Should we give you an honorary degree as
Yeah, I think so.
theoretical
I think so.
physicist?
I think so.
Yeah, we can start the procedure.
And so with this, I would like to thank you for coming here even on a Friday. And if there are any questions, I can try
Yeah,
to
thank you
answer.
very much for the great talk. Are there questions for Marco?
I have some questions, but I don't know whether to other people have some. So I have quite a few questions.
Yeah, go ahead. Just speak a bit towards the microphone.
Okay,
so that the other people can hear.
Could you go like back maybe 4 slides, I think, to the bit where this one, I think. So I was trying to see, so the requirement to have when you have in the limit that lambda goes to 0, you only need the sigma to be centered such that its expectation is 0. And then what's the effective temperature that you obtain? Like, do you obtain an effective temperature?
Yeah, the effective temperature is inherited from, it's obtained as follows. You calculate the matrix A, the covariance matrix of the beam splitter. Even though that's not, again, that's not a Gaussian statement, you can always calculate this matrix. This matrix will be off diagonal, and on the off diagonal you get a term, which is actually a non-negative term, and then that term is a given number, and that number, which is characterized by the sigma, the beam splitter, is equal to this quantity here. And this quantity carries the beta of the... So your sigma determines a number. That number is the off-diagonal density matrix. Then you solve this. This number equals 1 over e to the beta minus 1. Solve this for beta. That is the temperature that your final state will be at.
Yeah. So I guess from like a thermodynamical perspective, you could, I don't know, if you have a non-Gaussian state. Because I guess if your sigma are Gaussians and they're thermal states with some fixed temperature, you're always going to get your
you get the same.
same
Yeah, of
temperature
course.
with
That's right.
your ancillars or your beams. But if you have a non-Gaussian state, you could prepare your system at either higher or lower effective temperature.
Yes, absolutely. Yes.
So that's something that you could calculate.
Yes, absolutely. Yes.
Yeah.
Yes. But basically, the thing is that the average number of excitations is the same of the outgoing state and the sigmas, and that determines the temperature of the final state.
Yeah, and the class of states which is stationary. Because I'm trying to think like what class of states. Obviously, if you have sigma, it's just e to the minus beta dagger beta, that's stationary.
That's stationary.
I was trying to think of what other class of states.
Anybody who commutes with where the number of excitations is preserved, they could use it.
Yeah. Is there yeah, I guess I'm thinking like, is there any indication how big this class of states is, or is it kind of very?
Oh, it's infinite, right? I mean, you take any matrix that commutes with this matrix n and make out of it a density matrix.
Yeah.
So you take all the projections of of B star B and mix them together any way you want. And I mean, I guess the question is what physical states do that?
Because I'm only ever used to working with thermal states, Gaussian states as thermal states, but
yeah, but sort of the whole point here is that you can have anything which is
so I was
stationary.
just trying to intuitively think what other states you could have that aren't a non-Gaussian but satisfy the.
Well, I guess a Fock state does that. If you have 10 particles,
Yeah. Okay.
its density matrix commutes with number of particles is fixed at 10. And so to lowest order, you will get a thermal state in the output. Not to all order, which is an example I had above. But the lowest order in lambda, the output state will be. So you can take a convex combination of Fock states.
Okay.
That should be that number preserving, I think so. Yeah, sure.
And Marco, can you do a statement for the case where the beam splitter is really 50-50? Not just everything goes through, everything is reflected, but half and half.
Well, everything is correct except then.
No,
this thing is not.
Yeah, but is there an analytical statement for that case?
You mean is there some special statement? Or?
Yes. If
I don't know.
it is 50-50.
I don't know, Francesca. I would have to think. I mean, whatever. This is all correct. You would have to see what this.
No, just if it simplifies to something nice in case it's 50-50.
Does this mean that sine equals to cosine, maybe? Yes, transmission equals reflection. Then this number and this is the same. So I don't know. Some stuff will happen. I haven't thought about it, but it
would be nice to know.
Why is 50-50 very special? Somehow maybe.
That's what usually beam splitters do.
Not according to Wikipedia, but
you
can have all kinds of this lambda you can tune. I mean, somehow. Okay, but okay. Oh yeah. Good. I don't know. Good question. One should see what that does.
Okay. I see Camille. Camille, do you have a question?
Yes. Yeah. Can you hear me?
Yes, we can
Yes.
hear you. We can see you. Not on that screen.
Okay. Nice. So yeah. Hello everyone. Hello Marco. Nice talk. I mean, yeah. It's actually it ends up being the same question as Francesco. Because I was wondering, so you managed to derive a limit for weak coupling, so lambda going to 0, and so let's say natural question would be in strong coupling, and so in this case, the strong coupling, I think it would be when so if everything goes through, it's more than strong and it's not interesting. And so maybe in this case, the strong coupling would be probably 50-50 or when you
Yes,
close
okay.
to 50.
Okay, I see, yeah.
And
Yes,
so, yeah.
That's a good point. I have to look at the expressions. In fact, yeah, it seems, I guess, yeah, probably the sign equals. I don't know. But yes, okay.
Sorry, what was the statement you had on the last? You said that in the asymptotic limit,
yes,
if the sigmas are thermal states, then it always goes. Maybe I misread it. If you go to the last.
If the sigmas are thermal states, then the final state of the thing that goes through is also thermal.
Even in the strong coupling regime.
Yes.
Okay.
Yes.
And Marco, has someone done the experiment? Because there's here burning to do the experiment.
If you want to become as famous as I am, you should do the experiment. No, I don't think so, Francesco. And also, a related question is, how many beam splitters do you need, right?
Yeah,
I mean, this.
How fast does it convert?
Yeah, exactly. So this technically
some
is.
statement?
I haven't also not thought about this, but yeah, it's controlling the limit of this.
Yeah.
Conversion.
In the lab, infinite systems, so we'll have to know finite.
I understand. Yeah, that's right.
Splitters
That's right.
that will make up the system.
That's right. So this can be, yeah, I mean, this, you know, can be turned by the logarithm into a series, and then you can estimate how many steps you need for an accuracy of 1% or something like that.
But you have a gut feeling for that, or not? Is it 1, 10, 100, a million?
Indicate how feasible the system is to build.
But that would be very nice to know.
Indeed, you're right, yeah.
The experiment would probably simple to set up.
Yeah,
You're
it's just based on.
Unless you need a
range
million
numbers.
beam splitters. Yes,
Yeah.
but, for 1, 10, 100 beam splitters, you could do that.
I don't know how many.
Okay, the afternoon is still long. So
Okay, but related, once you mentioned to me, maybe what if you have a ring of beam splitters, you want to use
yeah, you can do
So in principle here, it was important that, you know, your incoming state is product state, right? So you really would need many beam splitters, maybe, if this converges not so quickly or so. But now that I'm discussing stuff with Graham, it is also possible to do this if you have a bit of correlation between the beam splitters. So maybe having a ring somehow, you can also get this in a certain sense. With correlations. You want in the lab so many beam splitters. But it's true, I should, and I will try to estimate the convergence of that and see how many you actually need.
Yeah, that's nice. That would be interesting.
Yeah, the question.
Just this thing about the limit in small lambda again.
Yeah.
Well, I didn't understand the explanation of why you have to take the infinite beam splitter limit first and then small lambda. Is it?
Well,
Is the lambda like time dependent or something then?
No, lambda is not time dependent. I mean, so you have two limits: number of interactions and lambda. One you go let become large, and the other you let become small. So you have two choices: do the first one and then the other, or do it the other way around. What happens if you do it the wrong way around? First you take lambda to 0. It means lambda is a property of the interaction. In each interaction, if lambda is 0, it means the two beams, they don't see each other, they don't interact at all. So the output state of the thing that goes through will be equal to the input state. And now you can take the number of collisions to infinity and nothing will happen. Okay? But the point is, if you interact many times, kind of weakly, but many times, but weakly, you get this non-trivial effect.
That's interesting because I would have thought it should work both ways around, but
No. It doesn't.
It's
It's the same with the hot cup and the environment. It's exactly the same.
Yeah.
Because there, number of k taken to infinity is you waiting for a long time. And taking lambda to 0 means that you place this not on the table, but you have a styrofoam thing here, so that there is actually no interaction. Okay? Then this guy will not cool down, no matter how long you wait for the. Right? These two limits are absolutely not commutative.
Okay, other questions from our online participants? Please say it now or never. Or raise your hand or something. Okay. Doesn't seem to be the case. So, Marco, thank you so much.
Thank you, guys.
Brilliant talk. And maybe we are looking forward to see the developments.
Yeah, it would be cool, yeah.
Excellent.
Very cool.
Thank you very much. And thank you to all the guys online. And Camille, nice to see you again. Thank you. Thank you for following our
Bye.
webinars. Thank you.
Thanks for attending,
Bye.
everybody.
Bye, everyone.
Ciao.
Bye-bye. Cheers. All the best.